Well, happy Friday. Back with 483 and continuing on with centrifugal separators, and we'll also look at electrostatic precipitators today. So just a few reminders. The interim report is due on Monday at 11:59 p.m. and that includes your peer evaluations. So please make sure to submit both of those by 11:59. The participation question is open and will be open through 11:59 p.m. on Sunday. So don't forget to do that. And finally, the homework on gravity settlers, centrifugal separators, and ESPs, which we'll talk about today, is due on Wednesday at 11:59, and move that to Wednesday just so that the interim report and the homework we're not doing the same day. So let's continue that problem. I just want to go back to one mention here. When I set up this problem the other day, it was actually a similar problem in textbook. They actually had 350 Kelvin. What we solved was actually for 293 Kelvin, so it's about 20 degrees Celsius. And just had it been 350, then that would have meant that the viscosity and the density would have changed. And had that occurred, so let's just to go back here, is what we calculated was for a temperature of 293 Kelvin. If the temperature were 350 Kelvin, then we would need to adjust both viscosity and density, and that would have given a cut diameter of 6.5 microns, and that would result in a removal of about 67%. So notice when the temperature increased from 293 to 350, that actually results in a larger cut diameter. So it means that our 50% of removal occurs at a particle diameter of 6.5 microns rather than 6.1 as we had previously calculated, and the efficiency drops from about 69% down to 67%. So you do see when you increase the temperature, you see a decrease in efficiency. So I just wanted to mention that. I realized that after class on Wednesday, so I wanted to make sure that I did mention that. So we left off on Wednesday, finishing up the previous problem, where what we're doing is we're looking at what is the pressure drop across this gravity, across the centrifugal separator. So just to reiterate important parameters that we need, we said that the inlet height of this centrifugal separator is 0.5 meters. The width is 0.25 meters. The body diameter is is equal to 1 meter. The flow rate is 150 cubic meters per minute. And the gas exit pipe diameter is 0.5 meters. So if you remember, we obtained that information from the table that was provided for conventional centrifugal separators. So we had previously mentioned, go back to this slide here, that the pressure drop is a function of this term HV, which describes the pressure drop expressed in the number of inlet velocity heads. This term is the velocity head. And HV is equal to KHW over DE squared, so that inlet, sorry, the exit velocity. And this is equal to 15. We're assuming a K value of 15. So this is 0.5 meters times 0.25 meters divided by 0.5 meters squared. And that is equal to 7.5. And we had previously mentioned that about 8 was a reasonable value for H sub V. So that's right in the range of what we would expect. V sub I, we previously calculated as 1200 meters per minute. We need this in inverse seconds. And that is 20 meters per second. Delta P is equal to 1/2 rho G V sub I squared times HV. And that is equal to 1/2, 1.18 kilograms per meter cubed, 20 meters per second squared, times 7.5. And we need to do a conversion, and 1 kilogram meter per second squared is equal to a Newton. And that gives us a delta P value of 1515 newtons per meter squared, or 1.515 kilopascals. Okay, so that is the pressure drop. So the pressure drop across this centrifugal separator would be about 1.5 kilopascals. I'm going to add a slide in here, so we just have a little more space. We can now calculate the fluid power requirement. And we said that this is equal to Q times delta P. Q is given as 150 meters cubed per minute. We need to convert to seconds. We'll multiply that by the value we have in newtons per meter squared. And that is about 3,800 newton meters per second. And that newton meter is a joule. So that is a joule per second. And if you remember, a joule per second is a watt. So that is about 3.8 kilowatts. If we want to calculate the power that we need to supply, so that's the fluid power, we need to think about how much are we supplying to the fan and the motor. Typically that has about 70% efficiency. So it's 3.8 divided by 0.7, and that is 5.4 kilowatts, okay, which is means that we need about a 7.7 and a quarter horsepower motor to operate this system.
Hello, Professor.
Yes.
Hello.
Hi.
How do you transfer a kilowatt to the horsepower?
I just looked it up online actually to do a conversion, just a straight conversion.
Oh, okay. Can you show me? I don't know how to do that.
How do I do it? All I did was I went online, type in kilowatt to horsepower.
Oh, okay.
That's all I did.
All right, all right.
It's just a straight conversion.
Okay.
There's an equation, but it was easier to just look it up online.
Yeah.
And then just to finish off with centrifugal separators, just to give you an idea in terms of sizes, just gives you kind of a size range of some of these units. So you can actually see one on the truck, so you can get, it gives you some sense of how large these units are. And they're typically treating velocities, inlet velocities of about 50 to 60 feet per second, or about 15 to 20 meters per second, and have volumetric flow rates of about 500 to 1,000 cubic feet per minute. Okay, so that just gives you, I just wanted you to have some sense of the size and the both the pressure drop and calculating motor sizes. So any other questions? Sorry about I could pull up the conversion, but it's like I said, all I did was do straight conversion there.
Okay, can you show me the 24 page 24 again?
Page 24, sure.
Okay.
So the information here was all from the previous problem.
Yep.
Okay, and then the equations were given on slide 22. So this is straight from slide 22, and this is also from slide 22.
Okay, got it.
Okay.
Yep.
Good. Any other questions? This is why I like doing it online, because then you can ask questions. It kind of feels a little bit more like we're all in class together. No other questions? Okay, so let's move to electrostatic precipitators. I apologize. I just realized just before class that I hadn't posted the lecture. What I've done is, the last time I taught this course was in 2018. So I've posted the notes from 2018. So you have access to those ahead of time. Some of you have asked to be able to print those all in one. I'm modifying them a little bit as we go, and then I'm posting the new slides. So continuing looking at particulate removal, electrostatic precipitators are actually a very commonly used removal device in a number of industries. These include the power electric industry, power plants. If we could do a tour of the MSU power plant, you could actually see the electrostatic precipitators. Actually, really can't see much of anything because it's just a great big gigantic box, but you could see the size of these outside behind the power plant. They're also used in a significant number of other industries. So for instance, in cement processing, they're used to collect and remove kiln dust. They're used in the chemical industry, both to recycle materials. Those include metal. They're also used to remove tar. They're used in the paper and pulp industry to remove alkali salt, and they're used in lead smelters to remove lead from the fumes from these smelters. So electrostatic precipitators can be used for a wide variety of types of materials. So it's a versatile material treatment process. They can be used for both dry dust or liquid droplets. They tend to be used for liquid droplets where you have kind of a very sticky material, and that's to try and prevent that material from just sticking onto the collection devices. And we'll look at what those collection devices are. Basically, the force of collection acts on the particles, not on the gas itself that's carrying those particles. So the goal is actually to change the surface charge on the particles so that they migrate to a collection wall. These devices have very high efficiencies. You should be seeing the slides, and I thank you for asking that question. I apologize. Thank you. I'm sorry. You should be you're seeing the slides now, correct?
Yeah, we are.
Okay. I'm sorry. Okay, so just to kind of go back a little bit, this was what was on the first slide with a list of just treatment process, different industries, and then the next slide, it was just a little bit about the versatility of these processes. So moving on to advantages and disadvantages, as I started to mention, the electrostatic precipitators, or ESPs, have very high efficiencies, even for very small particles, which is why they're very commonly used in a wide variety of industries. They can also handle large gas flow rates, and one of the major advantages is that they have a very low pressure drop. As I mentioned previously, they can be used for both dry dust or wet collection, so for fumes and mist that contain water. They operate over a very wide temperature range. They also have very low operating costs, except at very high efficiencies. They can handle heavy dust load, and that should be dust. Dust loads, and they're extremely durable. They have a long service life with very little maintenance. The main disadvantage is the capital cost. They're extremely expensive to install, and they don't control gaseous emissions. So they will remove particulates, but they don't remove anything in the gas phase. So for instance, if you have sulfur dioxide, And particulates, these will remove the particulates, but they won't remove the sulfur dioxide. Or if you have particulates and NOx, they'll remove or the particulates, but not the NOx. The other problem is that once you have installed these, they're not very flexible if there are changes in flow rate, if there are changes in operating conditions. And this really became very apparent back when the acid rain program was first instituted, because what happened was these ESPs had been installed on a wide variety, a large number of power plants. A lot of these power plants were using high sulfur coal. So they're operating well, they're getting good removal of the SO2 particulate that's sorbed onto the particulates. Well, then they switch to low sulfur coal. And when they switch to low sulfur coal, they actually, the coal dust, the fly ash actually had significant different properties, and they got much poorer removal of the particulates and the SO2 on the particulates when they switched. So the SO2 that was in the gas phase, it didn't affect that, but it did affect particulate removal. And they actually had to add other chemicals to try and change the properties of that fly ash so that they could again achieve good removal. And it's basically a change in resistivity. So it depends on how the electrical resistance of that particle, if it is either very high or very low, you tend to get poor removal. So that's what happened. It's changing the coal actually resulted in a change in the resistance or the resistivity of these particles, and then they didn't get the removal. And it operates better at steady state. The other challenge with this is you've got an electrical current, so you have to be very careful. If you have gases that have a low fire or explosion explosive point, so that they're a fire or an explosion hazard, you need to be very careful using ESPs with those. So basically, the way that these work is that they're applying an electrical charge. So they ionize the particle, and so they're causing a change in the particle, in the surface of the particle. That causes the particles to migrate towards a collection electrode, so that they would migrate towards this collection of electrode. They collect on that surface. Then you can change the charge on this electrode. So basically what you're doing, then you're going to neutralize the charge. Then when you change the charge, you dislodge these particles, and you can collect them. And you can see that in this image here. You've got, in this case, you've got gases that are moving through this channel. You've got a positively charged collecting plate. So what happens, you can see here, you've got a negatively charged electrode that's across the center. You're going to charge these particles. They'll then move towards these collecting plates. They attach to the collecting plates. They'll then collect on these collection devices here, and then they'll be dislodged. So basically what happens is they vibrate these, that dislodges, and then you can collect the particles, and you can see this, and you've got these hoppers at the bottom. So gases are moving one direction, they're collecting along the side. When you vibrate these collectors, that causes the particles to fall into this hopper where they can be collected, and then they're removed. They're not really, well, they're an electric current that's applied to these. So they're basically an electrode. Okay, so this here, I just want to, so this is your negatively charged electrode. So as the particles move through here, you're changing the surface charge. So the surface becomes negatively charged. And now those negatively charged particles want to move towards that positively charged electrode. And then they collect in here. Does that make sense? Yes? Okay, good. Okay, so the equation that we use to describe the efficiency is referred to as the Deutsch-Anderson equation. And basically it demonstrates that the efficiency is dependent on what we refer to as the drift velocity. And that is the terminal velocity of the particles as they approach the collection plate when they're under the influence of the electric field. So basically, if we go back and we look at this diagram here, so we're applying, we've got this negatively charged electrode, we're applying an electric field. It's the velocity at which these particles are going to move towards this positively charged electrode and which is referred to as the collecting plate. It's also dependent on the total collection area of your electrostatic precipitator and the volumetric gas flow rate. So there's a number of assumptions that we're making, and just add another slide. It's a number of assumptions that we're making. One, that the gases and the particles move at constant volume, a constant velocity, sorry, okay, with no longitudinal mixing. The particles are uniformly distributed in Y and Z directions. This is in the X direction. So they're moving, the X direction is they're moving towards the plate, but they're uniformly distributed in the Y and Z directions. That the charging and collecting fields These are the electric fields. Are constant and uniform. So at any location, they are the same and they don't change with time. And that reentrainment is negligible. So once particles attach to that collecting plate, that's where they stay. They're collected. Now, the Stoich-Anderson equation is derived from a mass balance, and it's accurate. It's actually based on Stokes' law, so it's accurate for smooth spherical particles. This drift velocity is typically determined from pilot studies or from basically field experience with similar industries. So there's no good a priori way of actually determining that this terminal velocity that we use here. We rely on either pilot studies with the material to be treated and removed, or from field operations from similar industries. And this drift velocity, just to give you a sense of the range, ranges from about 2 to 20 centimeters per second. These are this drift velocity for coal fly ash. About 6 to 8 centimeters per second for sulfuric acid mist. About 6 to 7 centimeters per second for cement kiln dust. So it actually, for a lot of this material, for coal fly ash, it actually varies significantly. It really depends on the source of the fly ash, how that coal was processed. On the other hand, for cement kiln dust, the range is quite narrow. It's only about 6 to 7 centimeters per second. So we'll do an example here. And let's just insert a new slide so that we have it. Okay. So what do we have? We have a electrostatic precipitator, and it has 6,000 square meters of collector plate area. So just to give you an idea, a football field has about 5,400 square meters of area. So it's a little bit bigger than, in terms of the collection plate area, it's a little bit bigger than a football field. It treats flue gas and is achieving about 97% removal of particulates, and the flow rate is 200 cubic meters per second. So the question is, how large would that plate area have to be if we wanted to increase the efficiency to 98%, or if we wanted to increase it to 99%? So we've got 97%, but we would need, if we need to increase it, So 97% efficiency. Actually, let's just move this into the next. So we have 97% efficiency. We have Q equals 200 meters cubed per second. The collection plate area is 6,000 meters squared. And the efficiency is equal to 1 minus E to the minus WA over Q. So if we solve this, 0.97 equals 1 minus E to the minus, what we don't know is the drift velocity. So what we're actually really looking for is that drift velocity. This is divided by 200 meters cubed per second. And if we solve this, W is equal to 1.117 meters per second, or about 12 centimeters per second, which is right in the range of what we said for fly ash. So that gives us a drift velocity. Now that we have that, now we can set our efficiency to 0.98, and that is equal to 1 minus E. We have our drift velocity now. We're looking for the area, and we'll divide that by the flow rate. And if we solve this, the area is equal to 6,000, almost 6,700 meters squared. So basically we're adding about 700 square meters of area in order to increase the area so that we can achieve 98% removal. If we want 99% removal, then it's the same equation. Now we're solving for the area at that for 99% removal, and that is about 7,900 square meters. So we've gone from 6,000 square meters at 97% removal to almost 6,700 square meters at 98% removal to almost 7,900. So we had to add about 700 here, and we're adding almost 900. So it gets, the closer we want to, or the higher the efficiency we want, the more area we're going to need, and the more difficult it is to achieve that. I'm going to show you this figure right now. We've only talked about 3 of the different types of processes so far, but just to give you some sense, if we're looking at gravity settling, we're effectively looking at removing particles that are about 10, this is in microns, about, well, greater than 10 microns in size. So we can effectively remove particles greater than about 10 microns. If we look at cyclone separators, we're looking at removing particles that are between about 1 to 100 microns. If we're looking at electrostatic precipitators, we're looking at removing particles that are between about 0.05 to about 10 microns. So it just gives you some sense of the scale of the size of these particles. Often what you'll see then is, for instance, with an electrostatic precipitator, you may have a cyclone as a pretreatment to remove that larger material, and then your electrostatic precipitator is removing the smaller particles. We'll talk next week about fabric filters and wet scrubbers. But we'll end a little bit early today at this point here. So if anybody has any questions, happy to answer them. Any questions? Sorry about that just now with the slide sharing. If not, we'll end here. And on Monday, we will talk about fabric filters. Have a good weekend and stay well.